Hello, my name is Marcus Perryman. I'm a principal engineer on the Windows team at Microsoft. Windows on ARM brings the capability and breadth of the Windows operating system to these light, instant on, multi-day battery life, always connected and beautiful hardware. It's the same great Windows with the power and utility of a Qualcomm core. In this session, I'm going to explore developing and debugging your application on Windows on ARM devices. There are a number of other talks at the ARM Dev Summit, which might be interesting to you, looking at different aspects of Windows on ARM. And I've put them at the front because you may be interested in taking these first as an introduction before we go into the developing and debugging components. But I think probably the best place to start is to actually get a demo of the actual device and some of the things you need to set up when you're preparing to develop for Windows on ARM. So here we have my Windows 10 machine running Windows on ARM. You can tell it looks pretty much like any Windows 10 machine from that experience, but you can tell it's a Windows on ARM machine in a number of different ways. If we go to the About My PC, first of all, I can spot that it says the system type is 64-bit ARM-based processor, and in fact it tells me I'm running an SQ1 chip in this machine. Oh, and while we're here, just for information, I am running Windows 10 for most of the demos. A couple will look at on Windows 11, and I'm running 21H1 for those demos. Okay, another way you can see the same CPU information is in Task Manager. And if you go into there under the Performance tab, you'll see Microsoft SQ1 is listed as the CPU. And while we're here, something quite interesting about this chip, which is far more common on ARM devices, is that although in the SQ1 and in the SQ2 I have access to 8 cores, those cores are not equal. So there are 4 high-powered cores, which are in fact are the lower cores here on this graph, and 4 lower power cores. And the scheduler in Windows 10 and Windows 11 is intelligent enough to use those lower power cores for background tasks in order to preserve battery and allow the device to be available longer. Now that's something is useful to be aware of when running Windows on ARM applications, although it rarely is something you'll have to deal with. It's more relevant when you're developing and debugging, maybe running long-term processes on these devices, like a unit test or a acceptance test or a CI. Okay, so that's Task Manager. So the next question is, how do I set up my machine for development? Well, in many cases, you're actually done and you're ready to target this machine. But there is one place I'd like to take you again back in settings, which is the developer settings page. Now this provides a number of useful features, especially if you're developing universal Windows applications. There is a developer mode here, which allows you, when you switch it on, to target this machine with any unsigned applications or sign with a test file, which might be restricted in other circumstances. Now, as well as enabling the deployment of those packages, it also, you may have spotted, installed an optional package to this device, which is actually a subset of the remote debugger. And in this mode, when developing and debugging UWP apps, it makes connection with this device and deployment for debugging purposes much simpler. And there's that option for developer mode is paired with the device discovery. So if I switch on device discovery, this now allows me through Visual Studio integration to pair up the device with this machine for simple deployment and debugging from a remote machine. And I'll show you that later on. While we're here, let's look at the device portal. This can be quite useful for managing remote machines. So let's say you've got your ARM machine in a lab. By turning on the diagnostics, the device portal, you get access to a local host page and also remotely through the IP address or potentially from WSL through via Ethernet if you need to. And now that actually, let me look at that locally here. That device page provides you with some useful information for managing this device when you're not actually sat at it. So this is the terminal you'll see traditionally. You can see a list of the installed apps on that device. So if you've got utility apps, so let me just demonstrate that. Select the clock app and hit start. That causes a remote execution of that clock app, as you can see here. And you can also see on this page all of the running applications, and you can manage, kill, you can look at the CPU time and so on. So some relatively useful debugging information for the remote machine. And you can also use it if you need to deploy specific applications to this machine. And there's a lot of other information that's available, like performance, event tracing, debug information, and so on, that you can get from this remote machine through the terminal. As I said, that is also available remotely. We won't look at that at this time, but the experience is pretty much the same. Right, let's come back to the setting the machine up. So the first thing you'll want to do as a developer, of course, is to get yourself a command prompt to manage files and to know your way around the machine. And Windows comes with the traditional command prompt built in, which looks a little bit like this. And if you're familiar with it, it's very useful for navigating around. But of course, there are better tools. One of those tools I want to point you at is Windows Terminal. Now, Windows Terminal is deployed through the store. So this is the Microsoft Store application I'm running, and here is the Windows Terminal app. Now, one of the interesting things about Terminal is, or the useful thing we can demonstrate when we look at Terminal, is how do I know I'm going to get a tool that's actually running Windows ARM64 native? And that's quite important. If you're running debug tools that are long running and you need to make sure that the application is running efficiently and quickly, then you want to make sure that you install ARM64 native versions. And you can tell from store that you're going to get that by looking at the system requirements for an app. And under the architecture, you'll see that there is an ARM64 architecture listed. Now, if any store app has ARM64 as an architecture listed, then the store will deliver that version to your ARM64 device, and you'll be getting the best performance possible on that machine. So what is Windows Terminal? Well, I've got it installed here. If I launch it, it actually, for me, just shows initially the same command prompt as you see from the Windows installed version. But what this application does is allow me to collect a number of different command interpreters that you might be using, like PowerShell, for example. I can actually launch that, and it collects them in the same window, so I can manage them together. And the other advantages you've got with this is cut and paste. You can actually drag out text from here. It's got some neat font color features that you can edit and configure all through the settings within the application. So a very powerful environment. One of the things I want to show you is the Windows subsystem for Linux capability of Windows 10. Now, Windows on ARM also supports WSL, or Windows subsystem for Linux, within Windows 10 and Windows 11, but the experience on Windows 11 goes one step further. And for demonstrating this, I'm going to actually switch over to Windows 11 and take you through what it is. Now, Windows Subsystem for Linux is a full Linux execution within Windows. Let's switch over and have a look. So here we have my Windows 11 Surface Pro X device, and I've got Terminal running or available to run here. As you can see, I've got PowerShell up on there. Now on here, I also have Ubuntu installed in a WSL2 environment. Now WSL2 uses a virtualization technology for hosting the Linux environment. So actually, when I run this, I actually have full access to all Linux commands as if it were running on a Linux machine. And that's available on Windows 10 as well. But just to give you an example, I can actually install, let's try a simple package install, and then we can take a look. CPU. There we go. So we're running a simple command line Linux application within Windows at that point. But the thing about Windows 11, what it adds is the capability of running graphical applications as well. So here I've got gedit, and actually I'm able to run that within Windows. So I can do pretty much everything I could do on Linux. So if you've got Linux tools that are ARM based, then you can bring those over to Windows while you're developing your Windows app, and actually edit those or manage those right alongside your Windows installation on your Windows application. Okay, let's switch back to Windows 10. So here we are back on our Windows 10 machine. And before we end this demo, I want to just spend a minute thinking about web applications and web technologies. So Windows and ARM, obviously you can run web technologies through a number of different browsers, but not all browsers are running native, ARM64 native on the device. Although Chromium project supports ARM64, it's only Edge Chromium that I'm running here is optimized and shipping with ARM64 instructions for Windows and ARM. And that also extends to other web technologies like hosted controls, Electron and CEF. So if you're building and shipping an Electron app, then it's significantly valuable to upgrade to Electron 6.08 or above, which does support Windows on ARM. And for CEF, it's M88 is the key number to look for, which has supported versions of Windows of ARM64 builds. But two other things to call out. If you are using web content and you need to put that in your own app frame, then consider looking at the WebView 2 control, which is based upon the Edge Chromium project. Now, the WebView 2 control is available as a kit to download and install in your application, and you can see the details here on this landing page for WebView Edge. So Microsoft Edge WebView 2 control. It effectively embeds the Edge browser into your application within that window, and you can get all the information you need and the download packages from this page. And the other thing I'm going to mention, the last thing I'm going to mention, is actually PWA Builder. So maybe you want to ship your application or make it available as a progressive web app, PWA. Now, again, there's a really neat tool here for helping you prepare your application as a PWA and packaging it. If you go to pwabuilder.com, now that will also make use of the Edge browser inside of Windows and ARM to give you the best native experience possible for your web-based application. So take a look at PWA Builder. Okay, let's switch back to the slides. So on this slide, I've collected a number of the different things we talked about in that demo and the links to the relevant pages for further details. Let's switch over and think about the actual development tools available for building Windows and ARM apps, and also the relevant frameworks. So on the tool side, two primary tool chains we'll talk about today. Visual Studio, which we'll focus on how to get that set up a little later. Now that's had ARM64 support since Visual Studio 2017, which was version 15.9, and all the way through Visual Studio 2019 and on Visual Studio 22, which is currently in preview. That's our next major update. It introduces support for ARM64 EC, which is a new application binary interface, ABI, available on Windows 11 that makes it simpler for transitioning big applications piecemeal over onto Windows on ARM. And Mark Sweetgall's session later will tell you a little bit more about the ARM64 EC. Now, the other tool chain that's available is LLVM, or the Clang compiler. Since version 12, they've had native compile support on Windows and ARM, as well as cross-compile support. So if your open source project, if your project or your open source components require that, then you have a choice to build on the device or to build as a cross compile elsewhere. Now, the other two tools I'll mention today, VS Code is a fantastic editor that also provides an ARM64 native version available. It's web technology, and it uses the ARM64 version of the Chromium code base to provide that, and that gives you a great experience on the device or even on your developer Intel machine. Oh, and the last one we'll touch on is WinDbg, which provides a useful debugger separate from Visual Studio. If you want to do lower level debugging, it's very useful for that. Or if you want to do on-device debugging, it can be used for that as well. But our applications don't stand alone, and frameworks are important as well. And we need to make sure that if we're porting our application to support Windows and ARM, that the framework is available with the ARM64 support as well. And the good news is that the majority of frameworks that we use today are available. So WinUI and Project Reunion, looking forward, that's our new frameworks coming from Microsoft, will have ARM64 support out of the box. If your application is UWP or Win32, our compiler stack in Visual Studio will support, and the runtime will support ARM64 as well. If you're using .NET, then .NET Core introduces ARM64 support. WPF and WinForms was brought in with 5.0.8 and continues to be supported in .NET 6 Preview. So if you look at Preview 2 or above, you'll get support for ARM64. And on the open source side of things, the story is changing very regularly. Electron 6.08. CFM88, Qt is coming with 6.2 that will support ARM64. Boost has a lot of support for ARM in there already, although not completely. I mean, Boost is a very large library, and we know Lanaro is working on Python porting along with other people, and that ongoing work, I've included a link to that if you're interested or using Python. And that, as I say, that list is continuing to grow on a regular basis. Well, let's actually dive in and take a look at these frameworks and how I can get the dev tools set up in the best way possible for developing my application. So here we are back on the Surface Pro X device, and I've got my command prompt here. So let's first of all take a look at the .NET toolset. So as I said, with .NET 5.08, actually, we shipped an update to support WPF and WinForms natively on ARM64. And what that means is I have 5.09 installed actually, and we can actually see that if I take a look at .NET info. You can see in here I have the 400 SDK, which comes with 5.09, and I've got desktop and .NET Core support for 5.09. What that means is I can use the .NET tools directly to start developing actually on Windows and ARM. So if I do .NET new WPF, I actually use that tool to create a WPF solution here. If you look at what it creates for me, it's just a simple XAML app. Now, I mentioned before Visual Studio Code as being a very powerful editor that we can use actually on the device to efficiently edit code. And so what I can use is just literally run Visual Studio Code in that folder, and it gives me a folder view of the application here, so I can edit the different files. And you can see that .NET has created me a project file, a XAML file, some C# as well to sit behind it, and I can edit that pretty well on this machine. So let's just put something simple into our sample. So a text block. Let's do horizontal alignment in the center. Let's put vertical. The same. And font size. Let's put that up a bit. To 35, and as you'd expect, we'll say hello world to for our code in here. Okay, so we can save that, and we can go back to our command prompt. Now, because .NET 5 tools are built for Windows and ARM, it actually makes sense to compile. It ships a compiler with it, so I can actually do .NET build within that folder, and it'll go ahead and build my code. And spotted my error. Let me see if I can fix that. Let's do it properly. Text block. And there we go. I'm going to build that that loop on the machine. Right, now once that's done, I can actually go and look at the output from that, and you can see we've got devsummit.exe is built in there. Now, just to show you, it has by default built ARM64. I've also got installed on this machine the Visual Studio tools, which can be quite useful, although they're running emulated. They can be quite useful when you're doing a dev debug cycle, just to have them available locally. I'll explain why we're not using Visual Studio on this machine in a bit. But right there, if I run the dump bin tools on dev summit, let's do headers, we'll get the information that comes back. So what I've asked is to use the dump bin tool, which will look at the information on that executable, and it tells me that is actually compiled for ARM64. So we've built that as an ARM64. Let's actually go ahead and run it and see what we get. So there's my ARM64 application built locally on the machine and running on that machine. And that's, I mean, that's a reasonably tight dev loop that we can go through using code, using .NET tools to build it, and actually running it. But there is no debugger in that environment. Okay, before we leave this, let's just do one more thing. I wanted to show you how you can actually do cross compilation even on this machine. So .NET does allow you to build for different platforms, even though it is an ARM64 build. I can do a cross compile to x86, and if I go into my x86 output folder, we'll see in here again. Let's do a dump bin just to show what's happening. Where that came from. Okay, there's the dump bin. And you can see we've actually produced an x86. Now, because Windows 10 supports emulation, you'd expect now that application will run under emulation on this machine. But actually, because we're using .NET, it does actually require the runtimes. Now, on this machine, I've only installed the ARM64 runtime, and so it won't find an x86 runtime, which it needs to emulate as well. And that's part of the problem with performance of running x86 applications on Windows and ARM, is it's not just the code that you write that needs to be emulated, it's the framework libraries as well. And that's one of the advantages of ARM64 EC, which is coming with Windows 11, because in that environment, if you've got ARM64 bits and x86 bits, you don't have to, they don't have to match. You can actually mix and match them. Okay, that's probably enough here. What I'm going to do now is switch to my actual developer box, which is an Intel device, and we'll look at setting up remote debugging and a more productive cycle for things like Win32 and looking at the debugger. Okay, so here we are on my developer machine. I'm running Visual Studio 2019, and I've just created a really simple UWP application. Now, out of the box, when you use the wizard to create a UWP application in the current tool set, and for some versions before, you will get ARM64 support out of the box. So the targets will already be there. What I've done in this particular sample is I've manually stripped out all of the ARM64 targets from the project files and also from the solution file. So let's just put the same sort of thing in again so that we can test this out. Hello world. And in order to help with debugging, what I'm also going to do is put a button in the XAML and a handler in there so that we can just set a breakpoint. And we'll move that down using a margin. Okay, so we've got a bit of text and we've got a button. Let's do font size as well, so we can actually see the text. Right, so what we want to do, actually this needs to be text block. That's better. And the button, okay, the button's on the left hand side, that doesn't matter. So what we can do here is in the code behind, it's created the handler, and we can well, we just put breakpoint on that line. Okay, so that's our application. I can build it for x64 in the project configuration here, or x86. Now, if I've got an older project that doesn't actually have ARM64 like this one here, the way to add ARM64 is to go into Configuration Manager for this application, and under the Active Solution Platform, select New, and then we'll actually choose from the available ones. So with the UWP environment, it will provide you with 3 additional, any CPU or ARM. I manually deleted an ARM64. So if we select the ARM64 and suggest that we copy it from the x64, now the create new project platforms will actually create it for everything within the project. So if you've got multiple sub-projects and you want to create it as a solution target, then you'll need to specify or to select that. And it will add that throughout the project. And I'm going to go ahead and click OK. So that's now added ARM64, and I can control what it's going to do for ARM64. It's added it also for release. You can see I've got ARM64 here as well. Now that's pretty much all I need to do in order to add support for the compilation of ARM64. But what I'm going to do next is specify where we're going to run this. Now you'll notice that as I selected ARM64, the UWP environment knows that it can't run that locally, so it switches to device, but it does also give you remote machine as an option, and that's what we're going to do. Now for the UWP, if you remember, I mentioned before about the For Developers tab allowing me to pair between the two. Now at this stage with UWP, because I've selected remote, the first time I do that, it'll notice I don't have a machine selected for remote, and it'll show me the remote connections. Now on my network, although I have here Wi-Fi and wired network, I have my X3, which is my Windows 11 machine, which is wired network, and my X1, which is wireless network, are both showing up on the auto detect. So it's detected the fact that those machines are available and it can connect to them. I'm actually going to select the X1. Now, when we select that machine, it's now done and ready to deploy, although the connection has not yet been set up. Now, if at any point you need to change that, go into the debug properties here, and you'll see that the remote machine under debug has been set to X1. I can re-invoke that dialog by clicking on the Find button. Now, UWP takes care of all aspects of deployment for you, because of course as part of a UWP build there is a package step, and once that package is available, the deployment involves transferring that package and registering it on the remote machine. But like I said, the selecting the remote machine initially doesn't actually connect the machines. It's during the first deployment that you get this connection request. Now the handshake between remote and debug machine is done through a pin, and what I need to do now is actually go to my device or my ARM device, and I'll just show you that screen, and select the For Developers page again, and now click on pair to give me the number. Now back on the development machine, I'll actually go type that number in, you do get a limited time for doing it. Now, once that's done, you'll notice that I now have a paired device that's been successful, and the development machine is now completing the package. It's now going through the deployment. Now, what's actually happened at that step is Windows, with those debug packages, the optional packages we installed, gets a remote debugger installed on the machine, and the remote debugger has been responsible for allowing that debug connection and putting those things together. So here we have the application running. I can go back to my dev machine and put some breakpoints in to handle that click me. So let's go back and just reshare the screen from here. So here my application is now running under the debugger. I can come into this code here. I can set a breakpoint as you'd expect with all the debug capabilities, and then on my ARM64 machine, I'm just going to hit the click me on the handler, and we get the breakpoint at that stage. And we have everything we'd expect to have inside of this debugger. I've got the ability to query the sender, the routed event args, and so on. You've even got the immediate window if I actually want to execute code directly there. Okay, so next let's look at what a C++ application involves in terms of bringing that to ARM64. So here's my C++ project. It's just a simple app, command line based, that takes a couple of parameters. And as you can see, there's no ARM64 here. So it's the same process as we did for our UWP app. We go into the configuration manager, select new, and again, the toolchain offers me ARM64, copy it from x64. And again, we've got the option to create new project platforms, which will actually extend the ARM64 to the second project I've got in this solution. So I click on OK. That's done that. Just spot here the deploy option for this application does build as an exe is currently not available. We'll come back in here and turn that back on once we've got the debug scenario set up. Okay, so once we've done that, we now need to set up the connection for debugging, because it can't, Visual Studio can't debug this application locally. It can build it but can't debug it. So I go back in to this time into the debug properties inside of the project. So unlike UWP, when we're debugging C++, there's some manual steps we have to go through in order to configure the debugger. So we'll come in here and select the remote debugger, and all of this needs to be visited. So what we have here is the configuration for how it's going to deploy the application, how it's going to run the application, and how it's going to debug the application. And the various different commands need to be set. Now on my target machine, I'm going to create a specific working directory and a deployment directory that Visual Studio will copy the files into. Now you can use macros for some of these, but these macros are always related to the developer machine, not to the target machine. So I'm going to change some of these things. So we'll set it first of all up as remote drop, which is my target directory. The server name here is currently using my local machine. I need to change that, and it is Mark P X1, and I need a port number. Now by default it's 4024, but I'll go and show you where you can get that information from. Now for my debugging connection, I actually am going to turn off authentication. So Windows authentication is great if both machines are authenticated against the same trust authority, like, for example, both machines are domain joined, and then the security will be in place and be verified at the point where the connection happens. In this case, one of my machines is not domain joined, so I'm going to set that to no authentication. Okay, so that's my connection set up. I now need to tell it what it's going to run. Now to do that, I need to give a command and the executable name for the program that's going to start on the remote machine. So it's going to be in the same folder. Remember, this is remote, and it's core assign .exe. Now my application is command line takes a couple of parameters. I'm going to give it a command parameter in order to debug this. Okay, so that's the execution setup. I can select any number of different types of debugger. I'm just going to let it decide. It will pick native debugging. There's some other options in here. Now this option, the deployment directory, is about telling Visual Studio where to copy the files to on the remote machine. So again, it's a remote machine folder, /remote drop, a folder I've created on that remote machine already. And then I have further options to configure what else gets deployed to that machine as I'm doing it. So if I have a complex project, I can ask Visual Studio to deploy maybe some output from another process as it's going through that. And then the C++ runtime, I can control how that gets deployed. I've installed both the debug and the release CRT on my target machine already with CPU specific settings. Okay, so that's everything set up for my situation. I can now OK that, and my remote debugger is available to connect. Now remember, when we were creating the platform configuration, there was no deploy option available. Once I've set up that deploy directory, I can now go back in and turn on deployment for my core assign process, and that will allow the debugger, or tell the debugger, to build and deploy that package before execution. Okay, next step, I need to switch to the target machine, and we need to set up the recipient of that debug. So let me just share the target machines directory. Okay, so to make the connection, I'm not able to use for this particular setup the inbuilt remote tools that come with that optional package we use for UWP. I actually need to install the tools separately. Now the tools that you use are tied to the version of Visual Studio, so I'm going to search for Visual Studio 2019 remote debugging, and there's a page here which goes through all the details about how to set up remote debugging, and also provides the download links for each of the different packages. So I'm going to pick up Visual Studio 2019 remote tools, and in here I can choose processor specific tools in order to run them for configuration. So I would select ARM64, but of course I've installed those before, so I'll just use that remote debugger process that I created or installed before. So when I run that, you can see here is the port number I mentioned before, and also the machine name. So MarkPX1 4024 is the default listening port. First time you run this, you'll get a port challenge for Windows just to open up those with the firewall. I'm also going to turn off my authentication to match the machine that was the configuration I set up for my debug machine. And just to show you, I've created this remote drop folder as well to receive the files from Visual Studio. So let's come back to the developer machine and actually get the debug going. So if I click on debug or build and run, actually we probably need to do a single step because it's just going to run and stop. There it is. Right, so let's do an F10 instead, or single step, to get the breakpoint. So what's happened? Visual Studio has built the code, it has done the deployment to the machine, it's made the connection, and now I'm debugging through my program. So I can see I've got two parameters. I can, again, it's all the same debugging experience, whether it was local or remote, but I now have that set up and I can see my parameters, and I can debug the experience on this machine. Let's have a quick look at what it's done on the remote machine. And we'll just share that screen. There it is. So the process is running here, but you can see my debugger has picked up the connection. And if I look in the folder, the files that I need are actually been deployed. So I've got my core assign in here, and a number of the runtime files that are required to execute that process. And so now I can debug through and actually see what is going on. And this project's quite an interesting one because this is actually enumerating the CPUs and looking for the high powered cores and the low powered cores. Little project I've built to help configure what's going on. Okay, so let's finish that. Now, of course, the deployment, I can run that process locally anyway, because it's deployed it for me. But normally you would then take that C++, package it and provide it as an MSI or an MSIX, depending on how you want to package and deploy that. Right, let's carry on with the slides. So we spent a few minutes looking at setting up remote debugging and how we can do our porting. Why then do we look at remote debugging? Well, there's a very good reason. With a setup where your development is taking place on your developer box, your powerful developer box that you're most used to using, this is the most efficient and recommended way to do your tight dev cycle when you're building, deploying, and debugging. And it's also it's shown to be the least cost option when looking at migrating existing projects specifically onto ARM64, because in most cases developers have their environment set up, their machines ready, the investments in the powerful hardware for development, and that will give you the best way to add in ARM64 as an additional setup environment. And for your CI, so your continuous integration and your test cycles, that is still the recommended way, where possible, to continue adding the ARM64 to your existing your build pipeline, and then use a native test suite that sits on top of that. So actually doing remote deploy to the ARM64 machine, and then running the tests on that machine only at that point. So the compile happens as a cross compile, the test happens as a native test. Now the potential exception to that would be if you're using the LLVM toolchain, the Clang compiler and the various other tools. That does provide fairly efficient native compilation, and if your build chain needs to be native and you're using LLVM, then that can be a relatively efficient CI. Today though, with Visual Studio, the MSVC build chains, those are emulated on the device. So in terms of efficiency, the cross compile is still the recommended way forward. But you do need to purchase ARM64 hardware for when you're doing those tests. One of the advantages we have with Windows 11 is that we will support the VM or Hyper-V management console on those devices, so that you can create VMs for different projects and have those as the test target for automated deployment. There's a dev kit, so something else to mention, there's a dev kit that's been announced by Qualcomm. It's a pretty low cost option and will be quite attractive if you're looking at building and setting up your CI and your continuous test environment. So definitely worth tracking that. I've got a link in the slides that will take you to their announcement page. Just a word about other tools. If you are building drivers, then WinDbg is the tool that will probably help you get that set up, and the driver development kit is still the right way to go when you're developing those drivers for ARM64. And I've got a link again for the sysinternal tools, which are very useful. Many of them have been ported over to ARM64 for inquiring and setting up and testing on your ARM64 machine. So a few resources that are valuable there. So we've been talking about getting developer environments set up and how to bring your apps across to Windows on ARM. I want to spend a few minutes thinking about how we get the most out of Windows on ARM. And there's no surprise, we start with moving away from emulation. And we give our users of Windows on ARM a promise of multi-day battery life, of great performance, and always connected. But that multi-day battery life and that performance, really, that promise can only be delivered when we move away from emulation for all of our apps. Using native code or getting to native code does bring the best performance. It does bring the best battery life, and there are many different ways we can do that. You can jump in and do the port across today to bring your applications to Windows on ARM. And Windows 11, as I mentioned before, brings a new ABI with the ARM64 EC, making that move across actually not a big bang, but potentially gives you the option of taking it piecemeal, starting with the key components and expanding out your native piece by piece, mixing ARM64 and x64 binaries in the same process. So moving away from emulation is the key thing. That's also true for web-based applications. As I mentioned, Electron, if you've got an Electron app, look to move up to at least 6.08 and above, and then look at building an ARM64 version where the support is present from Electron to give that native experience. The same thing for CEF. It's M88 we need to move to, and if you're doing other web experiences, consider using the WebView 2 control, which will give you the access to the native or the inbuilt Edge Chromium ARM64 compiled browser. But all of these will give parity, bring us to parity. Yes, it will bring out the best battery life. Yes, it will bring out the best performance. But just a word about going beyond parity, and there are really just two things to call out here. We do have in our C++ toolset and in our C# toolset from .NET 5 intrinsic support for the Neon instruction sets on the ARM cores. So if you have got very tight loops or very performance dependent behaviors, then it's definitely worth looking at moving the critical code to intrinsic operations and get the most out of the chip that you're running on for ARM64. And the last thing to mention is that the Qualcomm chips that power Windows on ARM are system on chips. They're not just a processor, and there are various other bits inside of that silicon that provide additional capabilities. Now, for some of these, there are SDKs in development. Some SDKs are released, one of which I called out here. The Neural Processing Unit, or NPU, is something that Qualcomm make available as an SDK, and there's in the session by Qualcomm at ARM Dev Summit, they'll talk about this a bit more. So let me finish with a call to action, and no surprises. My call to action is go and get the tools and try your app out on Windows on ARM. You can get, from the links I've got there, you can get Visual Studio or Visual Studio Code. Go download those, they're free. You will need to get hold of some hardware. Take a look at the dev kit from Qualcomm for a low cost option there, or any of the many different Windows on ARM devices, including the Surface Pro X, to grab that, get a great consumer experience and test your device out. The call to action is go and add your ARM64 support to existing projects and make them available to users of Windows on ARM. You can grab the docs if you want to see how things fit together, as I've put the link there. And if you've got feedback on particular parts of the documentation or the toolchain, I've given you a feedback email alias that you can take a look at and send us your feedback. There are 3 other talks that are worth calling out on this subject that are worth calling out on Dev Summit. Harry's doing a high-level talk about our direction and our future. Mark's digging into intro and talking about ARM64 EC in a little bit more detail. And Rami's doing a session, Rami from Qualcomm's doing a session that's looking at some of the other components in the system on chip that drives Windows on ARM. And that just leaves me to say thank you for listening to this session, and I hope you enjoy the rest of Dev Summit.